example 16. Okay, remember this, let me go back to, there is this example. Which example is it? Example 7. Okay, example 16 is similar to example 7. Okay? Remember the same approach that we took for example 7. Okay, if you don't, so when you revise, when you read through, make sure you read example 7 first. Then if you understand, then example 16 should not be a problem. Similar approach. Now, wait, let me do something. Do I have this? No, I don't. Okay, never mind. Use an algebraic approach to show that C lies entirely within the region bounded by the lines. Okay, algebraic approach. Okay, I'm going to do this. Y equals to half. Y equals to negative half. What you want to show is the graph of C, no matter how it looks like, it only exists here. It doesn't exist here. Am I right to say that? That's what you want to show. Use an algebraic approach. So, let us try and find. We want to show this. So, I really don't know how the graph looks like. It can be like that. I don't know. I really don't know. Of course, it's not like that. If I substitute a value, substitute y equals to, say, 1/4, I will surely get an intersection with the graph. I'll get a solution. Okay? I'll get a solution. So let us do this. I substitute one real value of y inside, I get a quadratic equation next. Can you have attention, please? There's not much copying, so all look up. I say one more time. I don't care how the graph looks like, I want to show that it lies between like that. So I'm going to substitute one y into this, rearrange, I get a quadratic equation in x. Now, in order for me to cut the graph, that means there is some graph that exists, there must be real solutions in x. So for real solutions in x, discriminant must be greater or equals to 0. That is the main idea. Remember, we have done it in example 7. Okay, so I'll move a bit faster. So if discriminant is greater or equals to 0, you realize that in order for a horizontal line to cut the graph, the horizontal line must lie between negative half and half. So there we have shown it. Do you follow what I'm saying? Okay, good.
So are you trying to find if it's 1, 1?
I'm not trying to find whether it's a 1, 1 or not. I'm just trying to find whether, I'm just trying to prove that as long as my y lies between negative half and half, I will have a solution in x. Correct? That's what I want to prove. Okay? So now we are done that. Then we want to sketch C. Okay? We want to sketch C. How do we find, how do we sketch C? First, we go through the things that we want to find. Intercepts, 0, 0, no problem. Let's accept that. Stationary point is a bit, okay, like I said, a lot of things are printed for you because we want to save a bit of time. I think the simpler stuff, I don't think we want to spend time copying, but let us focus. I'm sure we can differentiate it. I will leave it to you. Okay, you get something like that. Our objective, let's accept from here, dy dx is this. Our objective is to find dy dx equals to 0. Do I need to worry about the denominator? No. So numerator equals to 0, I get two solutions. X equals to plus minus 1. I will get two stationary points. Are these stationary points maximum or minimum? Don't need to worry to check second derivative test because the GC will tell you. Do you follow what I'm saying? The GC will tell you whether this is maximum or this is minimum. Doesn't matter. because they didn't ask you to show algebraically, they only asked you to sketch. So go to your GC and your GC should. And then of course asymptotes. Is it obvious to all of us that this is a proper rational function? So therefore, what is the horizontal asymptote?
X-axis.
Y equals 0, very good, x-axis. Okay? So y equals 0 is a horizontal asymptote. There is no vertical asymptote. Make sure you know why, because this can never be 0. The denominator can never take on 0. Make sense? Okay. Then we go to our GC directly and get this shape out. Then it actually all makes sense, you know. You see very carefully. Okay, let's do this together. I think it's worthwhile to do this together. Okay? Okay, try, all of us take out our GC and try this together. X over x squared plus 1. Oops, plus 1. All right. Okay, did you get that? Let's try zoom 6. What do we get? Die. GC spoiled. Okay, clues. Now really tips. Clues. Look, you know that y is bounded by negative half and half. So, and you know that your standard window setting is from negative 10 to 10. Of course, you say GC is spoiled because negative 10 to 10, but actually the graph only exists from negative half to half. So it's all compressed. The scale is wrong. So how do we see it? We see it like that. From negative, say 1.1 to 1.1. No, not 1.1, 0.6, sorry. Negative 0.6 to 0.6. They're not spoiled. Do you follow what I'm saying? Okay? So, from here it all makes sense because it's bounded by x equals to negative half, y equals to negative half, and y equals to half. Then we have two stationary points up there, and then we have asymptote, y equals to 0. All makes sense. Now let's try and find the, if we had not found the maximum and minimum point algebraically, can we find it by GC? Yes. Okay? Second, calculate. Let's say I want to find the maximum point 4. That means I want to find this one. Okay? So left bound, enter. Right bound, enter. Okay, now it's really interesting. I don't think this is the first time I say this. GC spoil again. GC spoil again. Why do I say that? Look here very carefully. It's 1.00006. And then what? That means what we are saying, the coordinate is 1.006, 0.5, half. GC spoil. Because our analysis tells us that when x equals to 1, it's a maximum point. Correct? Correct? It's the GC spoil. So who is correct? You say GC is not spoiled, so who is correct? Sure or not? The GC very clever leh. Very good, you are cleverer, very good. Yes. Okay, look. How does the GC work? Again, I repeat, GC is not clever. GC is just very fast. So what the GC did is, I sub x equals to 0.5, then 0.6, 0.7, 0.8. Then compare whether which y is bigger. Then of course it stops somewhere, maybe 1.00006. Y is somehow numerically they found that y is quite big, y is maximum. So sometimes some errors can happen. Okay, the GC just do iterations. So in this case, you don't trust the GC whenever, especially when you see things like 0.006 or 0.999999, which is what you see on your notes. You see, even it's from the same GC, you get different numerical errors. You know what I'm saying? See here, you get 0.999, Then you got 1.0006. What? Okay. Anyway, done, huh? So you get this. Okay, just a few notes. This one is not so bad. What this point, if you have finished sketching all lookup, the tail ends are shown to approach the x-axis. This part, be very careful. Can you check your friends? Please, they should not touch your x-axis. Check, check, check. Help your friends. Okay, because it's an asymptote. All right. With poor window settings, the GC may trick you, but in my case, because I'm quite good at GC, I won't get tricked by GC. You should not. Okay, so sometimes you will see that it coincides with the x-axis, but you know by analysis that the x-axis is an asymptote. Okay. Okay, can I use this example to say one point? Jot down if you need, because it's not really in the notes. Remember when I define asymptote, I say that asymptote is a line where the curve tends closer and closer towards without touching it. Correct. Okay. Now, if you observe, in this case, this line is the asymptote. But the graph actually intersects the curve at 0, 0. Curve actually intersects the asymptote at 0, 0. Now, so let's take the definition of asymptote very clearly. It is actually where at the tail end, the graph behaves like, tends towards the asymptote without touching it. Whether in the middle, no, it can intersect 10 times for all I care. Do you follow what I'm saying? Because when we define asymptotes, means when x tends to infinity, y tends to that value. That means here and here. But in between, it can cut 20 times or 10 times, it's fine. Do you follow what I'm saying? So don't be too worried if it cuts here. Okay? Okay, example 17. 2 more examples and we will finish the chapter.